Hi everyone, I'm Kenneth and we're with our Group FT8 and we're talking about spam email detection using machine learning models. So we're talking about introduction, background theory, solutions, and conclusion for this presentation. So for introduction, we all know that email is a main primary communication tool for today's world, but that also makes it a more main target for spam emails that can pose a security threat. So as you all know right now, the traditional methods of filtering out these spam emails can't really keep up with the evolving way of how it goes through. Hence why our group has decided to use a machine learning contributions in order to have a way to effectively filter out these spam attacks. So our project goal is to compare and evaluate the different machine learning models, and then you can also measure out the different model performance in order to help better combat these attacks. And then we hopefully would like to explore feature engineering. Now I'd like to pass my time on to my group members.
Thank you, Ken. I'll be going over the background theory of spam detection. Spam detection is a binary classification task where uh, spam emails are labeled as 1 and ham 0. The goal is to train a model that can learn a decision boundary to minimize misclassification and generalize well to unseen data. These models eliminate most of the probability of an email being spam. First is logistic regression. It is linear, simple, and fast to train. It provides a good baseline for comparison. Next is random forest, which uses multiple decision trees and majority voting. This reduces overfitting and handles noisy text effectively. Finally is the support vector machine. It finds the best hyperplane to separate spam from ham and uses the kernel function to capture non-linear relationships, performing well with high-dimensional TF, IDF text features. Next is the data pipeline overview. The process begins with the input layer where emails are collected from servers and metadata like subjects and body are extracted. Then the processing module cleans and prepares the text through low casing, punctual removal, tokenization, and feature extraction using TF-IDF to convert it into numbers. After that, the detection engine applies both rule-based filters and machine learning models to classify email or assign a prompt probability. Finally, in the output layer, email spams are flagged and user feedback like marking messages as spam helps continuously improve the model's accuracy. Next, I'll be handing over to Hannah.
Thank you, Praveen. Now to begin the solutions evaluation and discussion session, I will continue with the dataset overview. For this project, we used two well-known datasets commonly referenced in academic spam detection research, the link spam dataset and the spam assassin dataset. The link spam dataset contains 24 12-ham emails and 431 spam emails from a linguistic academic mailing list. The spam assassin dataset contains more than 6,000 emails collected from real inbox and user submissions, with around 31% of spam, including promotional and phishing type messages. It is suitable for testing spam filtering systems. After preprocessing all the data, we transform the text into numerical values using TF-IDF, which stands for term frequency inverse document frequency. TF-IDF combines two values. TF measures how often a word appears in one specific email. The formula takes the number of times the word appears and divides it by the total number of words in that email. IDF measures how rare a word is across the entire dataset. The formula takes the total number of documents, divides it by the number of documents that contains the word, and applies a log function. The final TF-IDF score multiplies both values, meaning a word gets a high TF-IDF score only if it appears frequently in one email but not across many others. This helps highlight spam-specific keywords such as winner, offer, unsubscribe. After TF-IDF generates the numerical vectors, we proceed to the model training step. So now I'll hand over to Kim Anh, who will explain the model implementation.
So I'm Kim. I will discuss about the model implementation. I will introduce you about our training environment that we use Python as our programming language and powerful libraries to perform the data processing, analysis, visualization, and machine learning. After repairing and reprocessing data, we move on to the model learning building by the circuit learned. So we trained three models: logistic regression, random forest, and HGD classifier. So we use cross and entropy loss function for logistic regression and random forest. With the logistic regression, we use LBFGS, also well known as the Gaussian-Newton optimizer. And for the random forest, because it is an ensemble model, so it's not required the optimizer. Lastly is HGD classifier. We use hinge loss function and SGD, stochastic gradient descent optimizer. Next, let's move on to the evaluation metrics and methodology. So we start with accuracy, which is measure the proportion of correct prediction among total prediction. And next is precision, is calculate the true positive prediction among the all positive prediction. About the recall, it is to measure the ability to find all the actual positive, and F1 score is evaluate the model trade-off between the precision and recall. Lastly is the confusion matrix, which is show the amount of correct and incorrect prediction about ham and spam of each model. So next I will pass the mic to my friend KA to discuss about the result of our model.
Thanks, Kim. I'm Kawing and I'll be discussing the training and evaluation results for the three models: logistic regression, random forest, and support vector machine. We trained and evaluated our models twice using two different datasets. I'll start off with our first training scenario. We used the linked spam dataset with a collection of 2,893 spam and non-spam messages, and the dataset was split for training and test in an 80-20 ratio. This is the classification report generated by our models for scenario 1. From the table, we can see that for all three models, the ham precision, recalls, and F1 score achieved more than 0.99 across the board. However, in the spam recall, for logistic regression and random forest models are 0.91 and 0.90 respectively. This translates into roughly 10% of the spam messages were not caught by the logistic regression and random forest. On the other hand, support vector machine had a score of 0.98 for spam recall, correctly classifying 98% of spam mails. This is the classification matrix generated by our models for scenario 1. From the matrix, we can see that all three models classified the 487 ham messages correctly. For logistic regression, out of 92 spam messages, only 84 were correctly classified. Support vector machines identifies out of 92 spam messages, 90 were identified as spam messages, while random forest identifies out of 92 spam messages, identifies 85 as spam. As we noticed in the first scenario, the logistic regression and random forest models were underperforming, likely due to the small data size. Hence, in the second scenario, we decided to add in a second dataset, the spam assassin dataset, to increase the training data for our models. The dataset increased to 8,689 messages, and also increased the percentage of spam messages from 16.6% to 27.4%. This is the classification report generated by our models for scenario 2. From the table, we can see that for all three models, the ham precision, recalls, and F1 score continued to achieve more than 0.99 across the board. However, the performance of logistic regression and support vector machine remained consistent in the spam recall, spam F1 score, and spam precision, while random forest spam recall had a 7% increase in spam recall performance. This is also reflected in F1 score improvement from 0.95 to 0.98 and the overall accuracy achieving 0.99. From the confusion matrix table in scenario 2, the evaluation dataset, there are a total of 1,281 ham messages and 457 spam messages. Logistic regression incorrectly classified 2 ham messages and 18 spam messages. Support vector machine incorrectly classified 2 ham messages and 9 spam messages. Random forest incorrectly classified 1 ham message and 14 spam messages. In this table, we are presenting the spam false negative rate in each scenario. So we can observe that for all three models, the false negative rate has decreased with a larger dataset and a greater distribution of spam messages. Random forest and logistic regression improved by 4.5% and 4.8% respectively in the classification of spam messages, while support vector machine had a negligible improvement of 0.2%. These are the key insights gathered from the evaluation of the models. Firstly, all models excel on ham predictions. The F1 scores were over 0.99 in both scenarios because of the imbalanced distribution of ham and spam in both datasets. with ham dominating 83.4% in scenario 1 and 72.6% in scenario 2, the models can predict ham most of the time and still look accurate. Secondly, the larger and greater distributed dataset led to more diverse spam examples and thus led to improved performance of spam classification. Notably, random forest experienced a huge recall boost from 0.90 to 0.97. Support vector machine maintains consistency across both datasets regardless of data size or added noise from the imbalanced distribution. As support vector machine uses margin maximization and dependence on support vectors, it focuses on finding the largest margin between classes rather than just drawing a line that minimizes error. It uses supporting vectors in the span and ham category using fewer parameters, reducing the sensitivity to outliers.
Thank you very much. And now to conclude this PowerPoint presentation, from the three machine learning models that we have highlighted and went through, the SVM shows that itself is the best overall model with the highest accuracy rate and the more overall balanced F1 scores. The random forest also follows closely along, but it's a lot suited for bigger data sets, which is a lot more complex as well. Logistic regression is also a very good model with a high precision rate and however, it has a low recall because of its missing spam email messages. Looking forward, we hope for different projects that will utilize our project as to explore more data balancing and use more transformer-based models so that they can develop more spam filtering system that can very much defend against the evolving threats of spam and phishing. Thank you very much.